Hi everyone, welcome to the session. These are the questions from Unit 7 and 8, which includes ray optics and wave optics. So now let us go to the question number 1 from the Young's double slit experiment. The given question is, in Young's double slit experiment, distance between the slit is 1 millimeter. The fringe width found to be 0.6 millimeter. When the screen is moved through a distance of 0.25 meter away from the plane of the slit, the fringe width becomes 0.75 millimeter. Find the wavelength of light used. Let us go to the diagram. It is a double slit. This is S1 and S2. S1 and S2 are the slits 1 and 2. The distance between the slits is smaller. At a distance D from the slits, here we have placed a screen on which the interference fringes will be produced. The distance between slit to the screen is denoted by letter capital D. So here small d is equals to, it is the distance between the two slits S1 and S2. D is equals to 1 millimeter. So this can be converted into, from millimeter to meter, 1 into 10 to the power minus 3 meter. And D1, let us take this D, will be as D1 in the first case. D1 is equals to D. Next, in the second case, according to the given problem, the screen is moved away by 0.25 meter from the slits. The second case diagram will be slit 1 and slit 2, the distance between them is D. So now the slit will be moved through a distance of, the screen will be moved through a distance of 0.25 meter away from the slit. So this is actually D. So this D2 is equals to D plus 0.25 meter. This is a screen. So now the fringe width found to be, so in the previous case where the fringe width, the fringes are produced on the screen. So these are the fringes produced on the screen. The fringe width in the first case, beta 1 is equals to, beta 1 is 0.6 millimeter. In the second case, the fringes are produced on the screen. These are the fringes. The fringe width in the second case, beta 2 is equals to 0.75 millimeter. So these are the given data. Using this, we have to calculate wavelength of light used in this Young's double slit experiment. So wavelength lambda will be question mark. So now let us calculate. We go to the formula first. We have fringe width formula. Beta is equals to lambda d divided by d. So this is the formula of fringe width. Beta is equals to lambda d divided by d, where lambda is greater and d is the distance between the slits and the screen, and small d is distance between the two slits. So in the first case, beta 1 is equals to lambda d1 divided by d. So here this implies, so lambda, the value of d1 will be is equals to d, and this will be divided by d. So this is equation 1. In the second case, beta 2 is equals to lambda into d2 divided by small d. So this is implies lambda into d2 value d plus 0.25 and this whole divided by small d. So this is equation 2. Now let us divide the equation 2 by 1. Divide the equation 2 by 1, we get beta 2 divided by beta 1 is equals to beta 2 divided by beta 1 is equals to lambda into d plus 0.25 divided by d. This is for lambda 2, and this divided by lambda 1, it will become reciprocal. So we will get d divided by lambda into d. And now here this d and this d get cancelled, and lambda get cancelled. Now let us take the cross multiplication. This d will be multiplied with beta 2 divided by beta 1. Now let us take the cross multiplication. Beta 2 divided by beta 1 into d is equals to d plus 0.25. Let us substitute the values of beta 2 and beta 1. Beta 2 is 0.75 millimeter. Millimeter will be converted into meter by multiplying 10 to the power minus 3. This whole divided by beta 1. Beta 1 is equals to 0.6 power minus 3 meter. Here also 0.6 millimeter is there. This 0.6 millimeter will be converted into meter, and this will be multiplied with d, and this is equals to b plus 0.25. 0.75 divided by 0.6 is equals to 1.25. 1.25 into d. 10 to the power minus 3, 10 to the power minus 3 get cancelled. 0.75 divided by 0.6 will be equals to 1.25 into d, and this is equals to d plus 0.25. So here 1.25d. So now let us take the right hand side d to the left hand side, then it will become minus d. This is equals to 0.25. 1.5d minus d is equals to 0.25d. This is equals to 0.25. D is equals to 1 meter. We have the formula beta is equals to lambda d divided by d. Let us take the cross multiplication. Beta into small d. This is equals to lambda into capital D. So therefore, lambda is equals to beta into small d divided by capital D. So wavelength of light is lambda is equals to beta is 0.6 into 10 to the power minus 3 meter into small d is 1 into 10 to the power minus 3 meter is whole divided by capital D is 1 meter. Therefore, lambda is equals to 0.6 into 1 is 0.6 into 10 to the power minus 6 minus 3 it becomes minus 6. Now the lambda value will be written in an angstrom by putting the zeros in front of 6. It will become 10 to the power minus 10. So this is equal to 6000 angstrom is the wavelength of light used in this experiment. So question 2 from unit 7 and 8. Here the given problem is a rigid beam of light. A rigid beam of light consisting of two wavelengths 4200 angstrom and 5600 angstrom is used to obtain interference fringes in YDSE, Young's double slit experiment. The distance between the slits is 0.3 millimeter. I mean this is small d, and the distance between the slits and the screen is 1.5 meter. This is capital D. Compute the least distance of the foil from the central maximum where the bright fringes due to both wavelength coincides. So this is our given problem. So let us go through the solution. So here we have the formula. The least distance of the fringe pattern from the central fringe is given by x n is equals to n lambda d divided by d. So here in the given problem x n1 is equals to x N. So according to this, let us write the formula. N1 lambda 1 into D divided by small d, and this is equals to N2 lambda 2 into D divided by small d. Actually this is given in the problem. Left hand side D and right hand side small d get cancelled, and capital D get cancelled. So N1 divided by N2, let us take the cross multiplication, and this is equals to lambda 2 divided by lambda 1. So let us write the values of lambda 2 and lambda 1. N1 divided by N2 is equals to the value of lambda 2 is 5600 angstrom. 1 angstrom is equals to 10 to the power minus 10 meter divided by lambda 1. The value of lambda 1, so this is the value of lambda 1, 4200 angstrom, and this is 10 to the power minus 10 meter. So 10 to the power minus 10, 10 to the power minus 10 get cancelled in the numerator and denominator, and these two zeros in the numerator and these two zeros in the denominator will get cancelled. So if you divide this, N1 divided by N2 is equals to 4 divided by 3. Therefore, N1 is equals to 4 and N2 is equals to 3. Fourth bright fringe in the first fringe pattern will be coincide with the third fringe in the second fringe pattern. Now let us calculate the least distance at which both the fringes will coincide using this relation. So now let us take any one value of n and calculate the least distance at which both the fringes will coincide. So using the formula xn is equals to n lambda d divided by d. So x n is equals to value of n is, let's take the first value n1 4 into first wavelength, that is 4200 into d. Capital D is 1.5. This whole divided by a small d. Small d is 0.3 millimeter. 0.3 into 10 to the power minus 3. Oh, sorry, here 4200 angstrom. This can be written as 4200 into 10 to the power minus 10 into 1.5. Now let us divide. Xn is equals to let us multiply 4 into 4200 into 1.5. This is equals to 25,200 into 10 to the power minus 10 and is whole divided by 0.3 into 10 to the power minus 3. 25,200 divided by 0.3 becomes xn is equals to 84,000 into 10 to the power minus 10. If 10 to the power minus 3 comes to the numerator, it will become 10 to the power plus 3. Then xn is equals to 84,000 into 10 to the power minus 7. So xn is equals to, let us move the decimal to the left side. It will become 8.3 into 10 to the power minus 3. Sorry, 8.4 into 10 to the power minus 3. So meter. So this is the least distance at which bright fringe due to both the wavelength coincides. That means xn is equal to 8.4 into 10 to the power minus 3 meter at this distance from the center maximum. Fourth fringe from first wavelength will be coincide with the third fringe in the second wavelength at this particular distance from the center maximum. Here the one problem is like this. In YDAC, in Young's double slit experiment, fringes of certain width are produced on screen kept at a certain distance from the slits. When the screen is moved away from the slits by 0.1 meter, the fringe width increases by 6 into 10 to the power minus 5 meter. The separation between the slits is 1 millimeter. Calculate the wavelength of light used. So let us go through the solution. Here I write the first diagram with Young's double slit experiment. It is a double slit, slit 1 and slit 2. The distance between them is D. So here D equals the distance between the slits is 1 millimeter. 1 into 10 to the power minus 3 meter. Here the screen is placed at a distance. This is a screen. The screen is placed at a distance D, capital D, from the slits. That D, in the first case, D will be equals to D. In the second case, and here the fringe width in this case beta will be is equals to beta. In the second case, the screen is moved away from the slits by 0.1 meter. By the time the fringe width increases by 6 into 10 to the power minus 3 meter. So now I draw the second diagram. So that is, it is a double slit, slit 1 and slit 2. The distance between them is small d, and the screen is moved away by 0.1 meter from the slits. This will be taken as d dash. D dash is equals to d plus 0.1 meter. The screen is moved away from the space by 0.1 meter as the previous one. Here the fringe width, the fringes produced on the screen, here the fringe width beta dash increases 6 into 10 to the power minus 5 meter. So here we are going to calculate the wavelength of light used. So we have the formula. Beta is equals to lambda d divided by d equal to 1. In the first case, fringe width formula will be equals to lambda d divided by d. In the second case, as the screen is moved away, the fringe width will become increased. That will be taken as beta dash. Beta dash is equals to lambda into d dash divided by small d. This gives to lambda. Value of d dash is equals to d plus 0.1 and this whole divided by small. Here now let us substitute the value of beta dash. In this case, the beta dash becomes beta plus 6 into 10 to the power minus 5. Beta dash, this is the value of beta dash. Here also we can write beta dash is equals to beta plus 6 into 10 to the power minus 5. So this is the value of beta dash. I have taken the value of beta dash here, and this is equals to lambda into d plus 0.1 divided by small d. So this is the equation. Now substitute the value of beta in the equation. Substitute the value of beta here from equation 1. Substitute the value of beta. Beta is equal to lambda d divided by d. So now the equation 2 becomes substitute the value of beta here. Beta is lambda d divided by d plus 6 into 10 to the power minus 5. This is equals to lambda. Let us take multiplication. Lambda into d, lambda d plus lambda into 0.1. Lambda into 0.1. Lambda into 0.1. This one divided by, this divided by d, and this also divided by d. So in the left hand side and right hand side, lambda d divided by d, lambda d divided by d get cancelled, and this is equals to 6 into 10 to the power minus 5. Now let us take a cross multiplication. This small d will be multiplied with this. This is into small d. This is equals to lambda, and this 0.1 comes to denominator of this. Here I have taken the cross multiplication. So therefore, have used lambda is equals to 6 into 10 to the power minus 5. The value of small d is 1 millimeter. 1 into 10 to the power minus 3 meter is 4 divided by 0.1. So lambda is equals to, this can be written as, this 0.1 can be written as 1 by 10. So this equation becomes 60 into 10 to the power minus 8. Minus 3 plus minus 5 is equals to minus 8. Therefore lambda is equals to 6 into 10 to the power minus 10 meter. So therefore lambda is equals to 6,000 10 to the power minus 10 is equals to 10 meter is equals to 1 angstrom. So this is the wavelength of light used in this